Yeah, so today we're going to talk about containers, Kubernetes, and Google Cloud. Before I start my talk, I'm curious, who is using containers today in production? Okay, there's a few people. And who's using some kind of container management platform like Kubernetes or something else to manage containers? So just a few? Good. So the motivation of this talk is basically, first we'll answer the question of why containers, because I still get the question, like people still want to know why we should even care about containers. And then after that, once you are running containers, you're going to need some kind of container management platform. And Kubernetes is one of the most popular ones. So I'll answer the question of why Kubernetes and what kind of building blocks it provides. And then I'm going to show the demos on Google Cloud. So throughout my talk, we'll talk about container engine and how we make Kubernetes really easy to run in the cloud. So that's the talk. So there's going to be some slides, and then I'm going to switch to some demo videos, and I'm going to show you things as we go along, so hopefully to keep it interesting. And if you have any questions, we have enough time, so feel free to stop me at any time, okay? Who remembers these? Yeah, okay. It always makes me happy to see more people who use these, because sometimes I give talks to like schools and stuff like that, and when they look at it, they're like, oh, we don't know what this is, and it's crazy. I actually started my programming hobby. I should say hobby because it was a hobby when I started, with the one in the middle. I didn't use the biggest one. And back then, like, I had a computer, and I had one disk, an MS-DOS disk. I would put it into my computer, turn it on. It will load the operating system. And then once I had the A prompt, I will take it out, and I put another one. It was either GW Basic or Q Basic, I think. I don't remember which one. And then I would just get into my development environment, and that's it. That's what I did. And the reason why I brought it up is that it was really simple back then, because all I had was one disk for my development environment, and then I also had a book on GW Basic, and I would just try to copy and paste code from the book to the computer and try to make it work. So that was kind of my Stack Overflow or the book. And sometimes I would be stuck. Because I want to do something, I would be stuck, and I would try to figure it out. Like I would spend like a couple of days basically trying to figure out how to do things. So it was difficult in that sense that I didn't have internet, I didn't have people to help me out. But at the same time, I liked the simplicity of those days where you could just focus on the problem that you're trying to solve. Now, since then, a lot of things happened. First, obviously, the internet. And then after the internet, we had all these amazing things like object-oriented programming, DevOps, machine learning, IoT, mobile, monoliths, microservices, all that kind of stuff. So it's kind of impossible to know everything now. So what I try to do is I try to pick and choose what I am interested in, try to learn them as much as I can, but then I also try to learn the spectrum of technologies at the high level so that I get an idea of what's out there so I can speak the language, but it's really impossible to know everything. But when you want to solve a problem today, you still start with the code. So today, let's imagine that this is a piece of code that solves some kind of problem that you're trying to solve. It starts with the code. It doesn't run on a disk anymore. So you usually deploy your code on some kind of machine. So let's say you got a machine. It can be your own machine or it can be someone else's machine in the cloud somewhere. And your code is running, which is great. But then you need to worry about redundancy, because what if this machine goes down, right? The whole system is down. So what you usually do is you duplicate your code on multiple machines. This way you have some kind of redundancy. So if one of the machines goes down, you still have some code running somewhere. But then the problem in this case is that these machines, they have IP addresses. So how do people discover them, right? So what you usually do is you create something like a load balancer that has a stable IP, and people getting to your system would go to the load balancer, and the load balancer will try to figure out which one is alive, and then will direct the traffic to the machine that's working. That's good, but then how do you know that your application is actually running? Because maybe the machine is running, but then your app is not running because there's a bug in your application. Maybe it's crashing. So what you do is you usually create something called health endpoints. In these health endpoints, you kind of check what it means for your application to be healthy. So you basically do the checks for your application, and maybe you check your database or you check your dependencies and make sure that everything works. And if everything works, you say, okay, my application is healthy. Otherwise, my application is not healthy. But something has to check these health endpoints. So it can be either the load balancer, or you can have a separate health checker that would check the health endpoints once in a while. And then once it determines that one of the applications is not running anymore, maybe it will take some kind of an action. Maybe it will bring down the machine. It will create a new machine with the code and stuff like that. So this is nice. It's redundant and it's resilient, and things are like, when things go down, someone looks at it and takes an action, so that's all good. But the problem is now this is living in a single zone, right? It's in a single zone, and if your application needs to run 24/7, if you cannot tolerate downtime, the zones can go down. Even with big cloud providers, sometimes the whole zone goes down. So what you do is you basically take the whole setup with load balancers and machines and health checks and everything, and you duplicate that to another zone, just in case that if this zone goes down, you have some kind of redundancy. Now, this is good, but then you have another problem. How do you keep track of the state in the different zones? Because you have some kind of state in your application, but you have two separate zones, so the state is kind of separated from each other. So what you do is usually, in a really simplistic way, you have some kind of a queue in the middle. So every time you write some kind of state in one zone, you try to write a message to the queue, and then maybe something from the other zone will pick up that message and apply that state to the other zone. So this way the two zones can stay in sync. And then if your application is successful, at some point you want to scale up, right? Just having 3 machines is not going to be enough. So you can scale up manually if you want, so you can add machines as you need them. But no one wants to do that because things today, especially today, most applications, they have a cyclic graph. So more people use it during the day and less people use it during the night. So what you need is some kind of elastic scaling, right? So what you usually do is you create an autoscaler. So you either write it yourself, or you use, if you are using cloud, most cloud providers, they have some kind of autoscaler that will look at some kind of metrics in your application. And then from those metrics, it will determine if it should scale up or if it should scale down. So this way, your application is more elastic to the load that's coming in. So that's great. I mean, now we have a system that's resilient, redundant, and we have 2 copies in 2 different zones. Things auto-scale greatly. That's good. But if you look at it, this is a piece of code that solves the problem, right? That's what we care about. And I don't know you. I mean, if you're an operations guy, maybe this makes you excited. But for me, the code itself is what I'm trying to do. The code is what's solving my problem. But in reality, all the other stuff is what I have to care about, right? And they're not optional because people want things to run 24/7. So I cannot just say, okay, I won't do this anymore, because people expect things to work all the time, right? Up until recently, there was no DevOps, so I used to write code and give it to operations team and say, just make this run, and it's not my problem, you figure it out. But now we don't do that anymore because we have DevOps, and we are in charge of our code from end to end. So we write the code, we test the code, we deploy it, we monitor it, and then if there's a problem, we fix it and we deploy it again. So the times of writing your code and just giving to testers and then from testers to operations, that's gone, right? So this is our responsibility. So what do we do? If I have to imagine how software development should be, I think there are some pillars that should be true today. The first thing is I want to be able to write code in any language, and I want to make sure that code runs exactly the same way everywhere. Because I think we've been going through these phases where we have different systems and different operating systems and different environments, and we spend so much time just trying to make sure that code runs exactly the same way everywhere, and it's never the same, right? Java, for example, they tried to make this notion true, like by writing once and running everywhere. But even with Java, I had so many weird problems on different operating systems and different kind of environments. So this should be true in 2017, I think. The second thing is your app should be optimally deployed and managed. So as an application developer, I should write my code, but then when it's time to deploy it, it should be optimally deployed on the infrastructure that I have, and it should be managed by someone. But I don't necessarily need to worry about this myself, because I think we should be beyond this point where we are worrying about this ourselves. There should be some kind of system that does this for me. And the last thing is all the resources that I need, they should be provisioned on demand when I need them. Because we shouldn't worry about machines, we shouldn't worry about ordering machines, we shouldn't worry about capacity planning, things like that. All the things that I need should be available as soon as I need them. And if I don't need them, they should go away, and I should only pay for what I use. So I think if we have these 3 things working together, we would be in a good shape. And if you look at what's happening in the last few years, I think we are kind of getting there. So the first notion of writing your code in any language and running it anywhere exactly the same way. That's what containers are trying to do. So Docker, Rocket, these container platforms, they're all trying to give you a context for your application to run. And this context is guaranteed to be the same no matter where you run it. The second thing about your app being optimally deployed and managed, that's the whole point of container management platform. So Kubernetes, Docker Swarm, Mesos, and many others, they all try to do this. They all try to take your containers and find a way to deploy it on the infrastructure that you have and manage it as well. So if something goes wrong, try to fix it, things like that. And lastly, all resources are provisioned on demand. For me, that's the whole point of cloud. So with Google Cloud, AWS, Azure, you are basically getting infrastructure on demand and things scale up and down elastically. So you don't have to worry about capacity and you don't have to worry about machines anymore. So I think we're in a good shape. Today we're going to talk about containers and Kubernetes specifically. And I'm going to show some demos on Google Cloud. But most of the stuff I talk about, they apply to pretty much any cloud and any kind of orchestrator, really. All right, so let's talk about containers. Why containers? Why should we even care about containers? We have enough things to learn. So do we need to learn containers? And do we need to worry about containers? And the answer is yes. And the reason why is that when you look at how we used to deploy software, it kind of looked like this before. First you had a physical machine, and then you would install the operating system, the kernel, on top. Then you would install a set of libraries that your applications need. And then you would install your applications on top of that, right? This model was simple: one machine, one operating system, one set of libraries. But it wasn't resilient enough because there was no isolation between your applications at all. So anytime you change something about the machine or the kernel or the libraries, you could potentially break any of these applications. Then came along virtual machines. The idea of virtual machines, as you know, is that on a single physical machine, you have multiple virtualized operating systems. So you are virtualizing operating system, libraries, and the application in a virtual machine. This way you have complete isolation between your applications, so you're not really affecting each other. But now, instead of dealing with one operating system, you are dealing with 4 virtualized operating systems. And these virtual machines, they're not small. They're usually gigabytes in size, so they're not so easy to create. They're not so easy to move around. They're not so easy to share. So most of the time, people use them at the time of deployment. They wouldn't really use them when they actually wrote the code themselves. So it was still like we would write our code without virtual machines for a long time. And then at some point when it was time to deploy, we would create the virtual machine and deploy it. So it wasn't really, our development environment and deployment environment was still quite different with virtual machines. With containers, we are basically trying to combine the best of both worlds. So in containers, you have a single machine and a single operating system. But we are virtualizing from libraries up. So your application and the dependencies of your application, it gets virtualized into what's called a container. And the great thing about these containers is that they're much more lightweight than virtual machines. So instead of being in gigabytes in size, they're megabytes in size. And they're very easy to create. They're very easy to run. And they're very easy to move around. So you can easily share them with people. So with this, you have isolation, but also you don't have to deal with multiple operating systems and the heavyweight of virtual machines. So what is a container? Just a lightweight way of virtualizing your applications. They are sealed and isolated, as I mentioned, so you can have multiple containers running together on the single operating system. So you can have tens of containers typically running on a virtual machine. They are very easy to deploy, and they are very easy to introspect, so you can actually SSH into these containers and see what's happening. And for me, the most important part of containers is that they are composable. So you can have, for example, you can have a base image that your application depends on, so that's your dependency. And you can build your image on top. And then if someone else needs your image, they can actually build on top of your image. So this way you can layer your dependencies. And these layers they're cached, so that if you already got this base image for one of your images, then your next image, if it depends on the same base image, it will already have that image, so you don't have to download them all the time. Docker is the most popular container platform, but there are others as well. Rocket is also one of them from CoreOS, and I'm sure there will be more going forward. All right, so what Docker did is basically the notions behind containers, they've been around for a long time. And at Google, we've been using containers for more than 10 years, something like 12 years. But Docker basically took those concepts and they made them accessible to everyday developers. The idea in Docker is that you create something called a Docker file. Docker file, it's an image blueprint. So basically, it's the blueprint of your application where you define your dependencies, you define your environment, and you define what happens when your container runs. And then Docker makes sure that that Docker file runs exactly the same way everywhere you do your application. So from the Docker file, you define your everything, and then from there you get a container, get an image, and from there you run your container everywhere Docker is. All right, so what I want to do now is I want to start with a really simple application, and then just show you the application first, and then containerize it using Docker. So just to show you what the process looks like. And then after that, we'll take this application and we'll deploy it to Google Cloud on Kubernetes and see what Google Kubernetes can bring for our application. So let's do that. I have videos on my application because I wasn't sure of the Wi-Fi. So let's just run the videos. So I am here in Google Cloud Management Console. And then in Google Cloud, there's something called Cloud Shell. Cloud Shell, it's basically a Linux shell that you get in the browser. And then with that, you can just connect to a Linux box right away and just write an application. So that's what I'm using here. I'm a .NET developer, so I'm going to use .NET. I'm going to write a .NET Core application, which runs on Linux now. So the .NET command line tool is already installed on Cloud Shell. So what I'm going to do is I'm going to use the .NET command line tool and create a really simple Hello World application that will take and containerize using Docker. So what I'm doing is I'm creating a folder called Hello World ASP.NET Core. So that's my app. And then in there, I'll just say .NET new-t web. So this creates a skeleton web application that I'm going to use. So as you can see, all the files are already created. One thing I need to do is I need to make sure that this application starts on port 8080. So I'm just editing the program.js file. And I'm going to add a single line that will say use URLs HTTP 8080. So this way, when my app starts, it will start on port 8080. So that's what I'm doing here. And maybe I can just go a little bit fast here. Yep, so I did that. And I'll do .NET restore. So this will look at the dependencies on my application and download them onto my machine. For Java guys, this is kind of like Maven, basically. It will look at your Maven dependencies and download them for you. So that's what we are doing here. We are restoring packages. And then once we get the dependencies, we'll run the application using .NET Run, just to make sure that it works locally. And then we'll containerize it using Docker. So we'll take a look at that as well. So we got the dependencies, and then we'll do .NET Run. And this will compile the application and make it run. So this is .NET running on Linux, by the way, which is, to me, still amazing because for many years, .NET only ran on Windows, but now it runs on Linux. So now I'm doing web preview, which is a feature of Google Cloud where you can just basically connect it to this Linux box where the code is running from the browser. So I'm connected, and then I can see my Hello World application that we'll use to containerize and run on Docker later. So that's the app. Nothing exciting, but it will serve as a base for our learning, basically. And then to containerize this application, first what we need to do is we need to get our application together into a single library so that Docker can call this library. So to do that, I'm calling a function called .NET publish-c release. So this will compile my application, and it will compile all of its dependencies, and it will create a single DLL. And we will use this DLL from Docker. So Docker will call this DLL. In the Java world, this will be like creating a jar file that Docker can call, basically. So this is getting the DLL ready. The next step will be to create a Docker file. So I need to tell Docker how to create my image and how to run it. So this Docker file will define everything about my application, the environment, and the dependencies and stuff like that. So we'll create that next. But first we need the actual DLL. So that should be done shortly. So we got that. So we'll go to the publish folder where the DLL is, and then we'll copy a Docker file that I already created into this publish folder. And then we'll take a look at the Docker file because it's kind of important in understanding Docker. So I'm just copying the Docker file, and then once I do that, I'll pause it so that we can take a quick look at this Docker file. So this Docker file defines what the image should be like. If you look at the first line, it says from Microsoft.NET 101 runtime. So as I mentioned, this is a .NET Core application. So I need the .NET runtime, .NET Core runtime. So this is the image from Microsoft that has that. So that's my dependency basically. I'm getting that image from Microsoft. The second line is copy.app. So that says copy all the DLLs in this folder to app folder in the container. The third one says working directory app. So when the container starts, the working directory is app. Expose 8080. So I'm exposing port 8080 in the container. Then I'm setting an environment variable called ASP.NET Core URLs. So this makes sure that my application starts on port 8080 in the container. And the last one is entry point. So what happens when the container starts? I'm calling .NET command line tool, and then I'm pointing to my DLL that we just created. So when you look at this, basically this is my dependency. These are my environment that my application needs. And this is what happens when the container starts. So with one file, I am defining everything. And the beauty of Docker is that it will basically make sure that all this stuff is set up exactly the same way everywhere. So with this Docker file, we need to first create an image. So that's what we'll do. And then we'll run that image, make sure it works. And then we'll push it to Google Cloud so we can use it from Kubernetes. So what I'm doing here is I'm saying Docker build -t means tag this image. And I'm tagging it with a special syntax. So the first one is gcr.io, because I'm going to push this image to Google Container Registry. So that's gcr.io. Then the second one is .NET Atamel, my project name. The third one is the name of my image, hello.net. And then I give it a version name as well. So this is version 1. And dot is look at here for Docker file. So now Docker is looking at this file, and it's going through the steps. The first step is to get my dependency. This is the Microsoft image. And I don't have that image, so it's downloading that image from Docker Hub. I'll get that dependency, and then we'll go through the other steps as well, set up the environment, set up the port, stuff like that. So we'll let this run. So this is usually the longest time it takes, the dependencies, but once we have that, we are just setting up the ports and environment, all that kind of stuff. So if we do Docker images, now we should see our image on our machine. And actually, we should see two images because this is my image and this is my dependency image that I downloaded as well. So we just want to run this locally, make sure that it works before we push it to Google Cloud. So to run it, we'll say Docker run. -d means run in the background. -p means port. So I'm mapping the port 8080 on my machine to port 8080 in the container. And then I'm just pointing to my image name, gcr.io, .NET-HTML, all that kind of stuff. So this will run my image locally. And with this hash, I know that the image is running. And then if I do Docker PS, I see that my container is running. And if I do preview on port 8080 again, I should see the exact same application. So nothing is different, except this is running within Docker now. So it's running within a container rather than by itself. Okay? So now the good thing is I can take this image and push it to any other container repository. So in this case, I'm going to push it to Google Cloud. To do that, I'm going to use gcloud, a command line tool that you can use to talk to Google Cloud. So I'll say gcloud docker push, and then just point to my image. So this will take the image that I have locally on my machine, and it will push it to something called Google Container Registry. So that's a place where you can, it's a private place for your project to store images. So I'll push it there, but you can also push it on public places like Docker Hub and stuff like that. So this will happen. We won't wait for this. But at the end of this, we'll have our image in Google Cloud, and then we can use it from Kubernetes, basically. So I'll stop this. All right. So containers are good. They give us a stable environment for our application. But by themselves, they're not enough. Because in production, you need to do all these things. So if you need multiple copies of your containers, so if you need redundancy, you need to actually run them yourself. Like Docker doesn't help for that. If you want to scale up because you have a load coming in, you need to do that yourself. If you need to scale down to save money, you need to do that yourself. If you have a new version of your application, you need to roll out that new version one by one to the containers. If there's something wrong with that version, you need to roll that back, right, in a consistent way. If you want to have resiliency, you need to have healthy endpoints, as I mentioned. If you want to have configuration and secrets of your application, you need to maintain that somehow, and you need to make sure that that configuration gets to your containers. So there's all these problems that you need to do in production, And just because you took your application and containerized it doesn't mean that they go away. They're still your problems. And that's why things like Kubernetes exist. Kubernetes and other container management platforms, they're all trying to solve these kind of problems in some shape or form. So let's just look at Kubernetes, because that's all I know. I don't know many other container management platforms. So Kubernetes, it's a Greek word. It means governor. And it's basically a tool, a system to manage containers in production. It's 100% open source, written in Go. It came from something called Borg. So as I mentioned, at Google, we've been running containers for 12, 13 years. And we have an internal system for container management called Borg. So people who worked on Borg, they learned from it over the years, and they created Kubernetes for the open source world. For me, the most important part of Kubernetes is that it supports multiple cloud providers. So you can run it on Google Cloud, you can run it on Azure, you can run it on AWS. You can even run it locally on your machine or in your environment. So if you start with Kubernetes locally, you get used to it, and then it makes it really easy to move that same logic to some other cloud provider if you want to. And in Kubernetes, there are machines, and I'll show you some of those machines, but you don't think about machines anymore. You think in terms of containers and applications, but you don't really think about virtual machines. That's not your concern anymore. At the high level, this is what Kubernetes looks like. So there's a master that manages the cluster, and master has many different things like API server, etcd for the cluster state, controllers to schedule containers, things like that. And there are nodes. So these are the actual machines where you schedule containers. But as a user, you don't really care about nodes. You talk to the master through API, CLI, or user interface. So you tell master what you want to be true, and master basically makes sure that is true by talking to the actual worker nodes. So in this containerized Kubernetes world, your service kind of looks like this. First, you have your code running in a container. So everything has to be a container in Kubernetes. And that code needs to be in some kind of registry, right? So you have your container image in a registry like Google Cloud Registry or Docker Hub or somewhere like that. From there, you create something called a blueprint for pod. So I will explain what a pod is, but basically it's a way to run containers in Kubernetes. So you create a blueprint, and then you tell Kubernetes what you want to be true. So in this case, there's something called replication controller in Kubernetes, and we are saying that we want 3 replicas. So we want to make sure that we have three containers running at all times. And Kubernetes, or more like replication controller, will look at the nodes that you have, and it will schedule these. It will create these containers, and it will schedule them onto these nodes. But how these are scheduled and how they are run is not your problem anymore. That's Kubernetes' job to figure out where to deploy them, which one makes more sense. So for example, by default, it will schedule them on separate nodes, but you can also tell Kubernetes, schedule these 2 nodes together onto this node. So there's many different policies that you can do here. So once the pods are running, you can label them with different labels, and I'll talk about what those labels are. And then you want to expose these to the outside world. So to do that, you create a service. So service is kind of like a load balancer for your pods. And people will talk to the service because service has a stable IP. And then from there, it will get to your pods running on some kind of nodes. So your microservice in this world is a combination of your code and the things that Kubernetes provides, the replication controller watching your pods, and the service that exposes your pods, and many other things that Kubernetes provides. So we'll talk about these as well. All right, and then I should take a break here and talk about Container Engine. As I mentioned, Kubernetes runs everywhere, so you don't have to use Google Cloud for it. But Google Container Engine makes it really easy to run Kubernetes. And I'm going to show my demos on Google Cloud. So I just want to take 2-3 minutes and explain you what Container Engine is, and then come back to Kubernetes. So Container Engine is basically Kubernetes as a service. In Container Engine, you can get a Kubernetes cluster by just running this one command. You just say gcloud container clusters create, and then give your cluster a name. And with this command, you get a Kubernetes master and Kubernetes nodes to schedule containers. So and all the networking and everything is set up for you, so you don't have to worry about that yourself. Then you can you run this command to authenticate your shell with Kubernetes. And once you do that, you can use kubectl. Kubectl is a command line tool to talk to Kubernetes. So you can say kubectl get nodes. So these are the nodes that are in your Kubernetes cluster. You can do Kubernetes get pods. These are the containers running in your cluster. And you can do things like resize. So you can say G-Cloud container clusters resize, and you can resize your cluster from 3 to 5, for example, in a really easy way. So it makes it really easy to get a cluster, but also resize it to more if you need more. And Container Engine basically manages your master. So Kubernetes master is totally managed for you, so you don't have to manage that yourself. You get backups and monitoring and restarts and automatic upgrades and automatic healing, stuff like that. And there's 99.5 SLA with the master. But also the actual worker nodes themselves, where you schedule the containers, they're also managed a little bit. And you get logging and monitoring by default. So everything that gets logged in the container, it will go somewhere called Stackdriver, which is the logging and monitoring tool in Google Cloud. And you can see all your logs and all your error information and stuff like that in a central place. Okay, so that's Container Engine. So in a short sentence, basically it makes it really easy to run Kubernetes. That's all it is. But you don't have to use it. You can use Kubernetes by yourself as well. So now let's talk about Kubernetes building blocks. So what does actually Kubernetes give us to make running containers in a resilient and redundant way in production? Let's look at those. So when you look at Kubernetes terminology, there's a lot, right? There's deployments and pods and volumes and labels and replica sets and probes and services, and there's even more. I didn't list them all here. So when you first look at it, you're like, wow, that's a lot. Like, how do I know all of this stuff? The good news is that you don't have to know everything. So if you know deployments and pods and service, then you're pretty much good to go. And then you can learn the rest as you need them. So you don't have to learn everything from the beginning. And also the other good news is that it's good that there's so many building blocks, so you don't have to worry about them yourself. So there's liveness probes to make sure that your pods are healthy. There's stateful sets for stateful pods. There's dim jobs for batch jobs, stuff like that. So all these are implemented already, so you don't have to actually worry about them yourself. So I think in a way it's good that we have all these building blocks, but you don't have to know them upfront. So everything in Kubernetes starts with a deployment. So deployment is a high-level construct in Kubernetes where you just say, give me a deployment with this container, and you point to your image. And then deployment creates, under the covers, a replica set. It creates a pod. It creates a service. It creates all the lower-level things that's needed to run your container. And we will take a look at what these are. But at the very high level, you basically start with a deployment. And from there, you get everything you need at the base level to run your container. So the first thing that Kubernetes does is it creates something called a pod. So a pod is basically a way to group containers if you want to. So normally, you create one container and just run the container by itself. But there are some certain use cases where you want to be able to group multiple containers. For example, in this case, there's one container called file puller that pulls some files from somewhere, and then it also has a volume. So its volume is kind of like a storage for pods, and then there's also another pod called web server that looks at the volume and then it serves those files to some other consumers. So you want these two containers and their storage to live together, and to do that, you basically put them in a pod, and this way, Kubernetes will schedule them together, and it will kill them together. So they always live together, basically. So it's a way of grouping them together so that they're scheduled together and they're always destroyed together. And as I mentioned, volume is pod scope storage. So it's a way to have some kind of state in your pods, and they can attach to many different things. So they can attach to Google Cloud Persistent Disks or AWS Elastic Block Store or Azure File Storage or a bunch of other things. So it's basically a way to get some kind of state in your pods. And then once you have your pods, you can label them. And you can label them as you wish. For example, here we are saying we have a label app equals my app. We have another label called phase that has prod or test as values. We have another label called role, front end, and back end. So you can attach as many labels as you want, depending on what kind of application you have. And once you have those labels, you can group pods together. For example, if you want to get all the pods of your application, you can just use this selector to get all the pods of your application. If you want to just get the front end of your application, you can say app equals my app, but role also equals front end. This way you can only get the front end pods. And these selectors are really important because in Kubernetes, every time you create something like a replica set or service or something like that, you use selectors to do that. So you label the pods and you select them, and that's how you group things together. All right, so you have your pods, you have your labels. The next thing that you want to do is create a service. So a service is kind of like exposing your pods to the outside world. So to create a service, for example, in this case, we are using a selector, and we are saying type equals FE. So all the pods that have type equals FE will be serviced by this service. And the service, it will have a stable IP, and people from outside, they will get to the service, and the service will run robin in different pods. You can also set a session affinity, so you can make sure that people, once they get to your pod, they will always go to that pod as well if you want. All right, so let me show you some of this, see how they work. So let's look at creating a cluster first. So if you remember, in the last step, we pushed our image to Google Cloud. So let's first take a look at our registry and make sure that our image is there. So if you look at container registry in Google Cloud, under here, it's hard to see, but you'll see that there's a name and there's a version. So that's the image that I just pushed. So we're going to use this image in Kubernetes later. First, what I need to do is I need to actually create a cluster. So to create a cluster, I'm using gcloud. I'm saying gcloud container clusters create. And then I'll give my cluster a name, hello.net cluster. And then I'm going to specify the number of nodes. So this is the number of nodes I want to have in my cluster to schedule containers to. This is 1, because this is just a demo, but usually you will have more. You will have like 5 nodes or something like that to start with. You can also specify the machine type of your nodes. So in this case, it's an N1 standard 1 machine type. But there's many machine types in Google Cloud that you can use depending on your application. And I'm also saying zone Europe West 1. You can specify where the cluster is living. In this case, it's living in Europe West. So with this command, you get a cluster, a master, and a single node to schedule containers to, and all the networking that comes with it as well. So I will fast forward here, because we don't have that much time. But at some point, you can see that the cluster is coming up. So within 5 to 10 minutes, you'll have the cluster running, and you can use to schedule containers. So that's how you create a cluster. If you want to create a deployment, then this is how it looks like. So our cluster is created, and I'm going to use kubectl to create a deployment. But before I can do kubectl, I need to authenticate my shell with Kubernetes cluster. So to do that, Google Cloud gives me a command to run. So I just run the command. And with that, I'm authenticated right now. And now I can say kubectl run hello.net. So the hello.net is the name of my deployment. I can choose that. And then I'm just pointing to an image. So the image, gcr.io, .NET Atamel. So this image is the one that we pushed earlier. So, and since it's in Google Container Registry already, I can just point to it with image equals. And with that, I can create a deployment. I'm also specifying the port that I want to make sure that it's available. So with this, we have our deployment. So if I do kubectl get deployment, I should see that I have a deployment created already. And then under the covers, deployment creates pods. So if you do pods, this is saying container creating. So it's creating a pod, a container, and scheduling it onto the nodes. If we do get pods again, now it's running. So within a few seconds, your pod is running. And if I do kubectl get replica set, and I'll explain what replica sets are, there's also a replica set created. And then if we look at service, we should also see a service running. But the service has an internal IP. It doesn't have an external IP yet, because we haven't exposed it yet to the outside world. We'll do that next. And that's it. So with deployment, you get everything you need at the base level to run your container. And now let's just open up our pod to the outside world. So to do that, we'll first make sure that our deployment is running, and our pod is also running. Now to expose this to the outside world, we'll say kubectl expose deployment and give our deployment name. And then I'll say type equals load balancer. So what this means is that we are basically telling Kubernetes to create a load balancer in Google Cloud, and then attaching that load balancer to the service. And then from there, we'll get to the pod. So that's what's happening right now. So if you do kubectl get service, we should see that there's a service and external IP is pending because we are creating a load balancer and the load balancer is not ready yet. So that's why it's pending. But usually after like 1 or 2 minutes, the load balancer is ready and we'll have an external IP. And with that, it will have a load balancer that will talk to the service, and from service we'll get to the pod. So I'll fast forward here a little bit. So this usually takes a couple of minutes. At some point, you can see that we have an external IP. So if we hit this IP, we'll see the same application running. But the difference right now is that this application is not running on a random Linux box somewhere that could go down at any time. Instead, it's running within a Docker container, and it's being managed by Kubernetes. And if something goes wrong, it will be restarted and stuff like that. So that's how you expose your pods to the outside world. And let me just go back to my presentation. Okay, I mean, if you think about it, all we did so far is we took our application, containerized it, and just attached a load balancer to it. But that's it, right? Like there's nothing special about it. So you might wonder, well, what's so special about Kubernetes? Well, what's special is that once you have Kubernetes manage your containers, you get a lot of resilience and redundancy features for free. So I want to go through those now. First, you get something called replica set. Replica sets, they're kind of like big brothers watching your pods and make sure that your pods are always running. So what you do is when you create a deployment, you get a replica set. And in this replica set, you have a selector. So this replica set is responsible from pods that have these labels. And then you also specify what you want to be true. In this case, we want to make sure that there are 4 pods running at all times. So replica set will constantly ask the API server how many pods I have. And if at some point we have 3 pods, it will schedule a new one. If it's 4 pods, it won't do anything. So it basically always make sure that there's 4 pods running. So for example, in this case, we have 2 pods, pod A and pod B. They're scheduled on 2 separate nodes, node 1 and node 2. If something goes wrong with node 2, maybe it goes down or something like that, replica set will determine that node 2 is not healthy, and it will reschedule pod B to node 1. So it will do that for you, so you don't have to worry about it yourself. So with replica set, you also get scaling. So let's say you have 3 pods running with the replica set, and you want to scale out to 4. You just run one command and just say kubectl scale replicas equals 4, and it will basically create the pod and just add it to your service, and you have 4 pods that way. If you don't want to do manual scaling, you can also set up auto scaling. So you can install something called Heapster into your cluster that will look at the CPU metrics from your pods, and then you can create a rule in replica set that says if the CPU target is 50%, or if average CPU is more than 50%, then scale up. And if the CPU target is less than 50%, then don't do anything. So this way, you can scale up and down using replica set. And then you can do canary deployments really easily with replica sets. So let's imagine that you have some code running the version 1 of your application, and you want to introduce version 2 of your application because you have some new code. You can create a new replica set with the version 2. So it points to the version 2 or your image. But the nice thing is that the service only looks at this label, type equals BE, as its selector. And all the pods, they have that type equals BE. So so you have 2 versions, version 1 and version 2, being serviced by the same service this way. So this way you can have a canary deployment, look at this, make sure everything works, and if everything works, you can do a rolling update. And rolling updates in Kubernetes is really easy. So let's say you have a replica set with version 1 that's being serviced by this service, and you're ready to do a rolling update. You literally go to your deployment, change your image from version 1 to version 2, and just hit save. And once you do that, this is what happens. Kubernetes creates a replica set with version 2. Then it will add a pod to that replica set. And this pod will be serviced by the same service because it has the same label. So basically, it will create a canary deployment. And if everything is good, then it will take one out here. Then it will add one there. Then it will take one out here. And it will add one there. And just keep going like this until all of the nodes are version 2. And And once everything is good, then it will get rid of this replica set. So all this happens with a single change. You just go to the deployment, change the version number, and this happens without you having to do anything special, which is nice. Because if you ever did this yourself, you know how difficult it is, you know. Especially if something goes wrong in the middle and you need to do a rollback, then it becomes a nightmare. All right, so let me show you some of this as well. So let's look at the replication first. So I have my pods running, and let's say I want to kill this pod, right? So I get the pod ID, and I will say kubectl delete and pass in my pod ID. So what will happen right now? And let me just pause here for a second. Now replica set is watching my pod, and it's making sure that there's one pod running. But once I delete it, replica set will determine that and say, oh, this pod is deleted. I need to have at least one running. It will create a new one, and it will add it to the cluster right away. So I just want to show you how quick that happens. So I'm deleting the pod. So the pod is deleted, but when we do get pods, you see there's a new pod with container creating already. So it already detected and creating the container. If I do get pods again, oops, I don't do it here. But within basically a couple of seconds, it will get a new pod running, and it determines that right away. So now I can actually rely on someone else to make sure that my pods are running, which is nice. If I want to scale out, so kubectl get pods, I have one pod running, and I want to have more pods. I will just do kubectl scale and deployment and pass in my deployment ID, hello.net. And then I'll just say replicas. So with replicas equals 2. Now I scaled from 1 to 2. So it's just one command to scale up. If I want to scale up more, same way. I can change it from 2 to 3. And then this one, it's pending because I only have one node, so it's trying to find a place for it. But if I want to scale down, I can just say replicas 1, and now I scaled down from 3 to 1. So you can see that scaling up and down becomes trivial with Kubernetes. And then rolling updates. So let's say I want to do a rolling update of my application. So update the version from version 1 to version 2. So what I'm doing here is I'm just editing a file that I have in my application. So that's kind of like my new version of my application. So I just changed this message, learn how to build ASP.NET apps that can run anywhere, to that can run on Google Cloud. So I just changed that message. So that's my new version. So the way you do updates in containerized world is that first you need to create a new library of your application. So that's what I'm doing here, .NET publish. Once I have the library, I need to create a new image out of it. And then I'll push that image to Google Container Registry. And then from there, I can use it in my Kubernetes cluster. So that's what I'm doing here. Create the library, and then I'll create an image afterwards, and then I'll push it to Google Container Registry. So I'll just fast forward this because it will take a little bit of time. So this is, I'm building my Docker image, just like before. And then when I look at my images, I have a version 2 of my image that I'm going to use. Of course, I need to push this image to Google Container Registry. So I'm doing gcloud docker push. So this will be pushed to Google Cloud. And then this is the important part. So now once the image is pushed, I should also point out here, but one thing to point out here. You can see that in here it says one part is pushed, but the other layers are not pushed. Because I only changed a small piece in my image, so all the things that didn't change, they're already cached. We only pushed the difference of it, basically, which is nice. And now I can use this image in Kubernetes. So what I'll do is I'll say kubectl edit deployment and pass in my deployment ID. And this gives me the YAML file that's basically defining my deployment. And all I need to do is I go here, and there's an images section that points to an image in Google Cloud. So this is pointing to version 1 of my application. I'll change it to version 2. And then once I hit save, then all the stuff that I show you about rolling updates will happen behind the scenes. And it happens really fast. So if I do get service and go to the external IP, I should see my app already being updated to the new one. So if you look at the text here, it already says Google Cloud. So that's how you do rolling updates. All right, how much time I have? I have 8 minutes. And there's even more stuff. So the stuff that I show you, it's kind of like the beginnings of Kubernetes, but there's even more. I don't have time to explain them all, but I just want to talk about them like 1 minute each so you know what they are. And then from there on, you can go and learn more about them. So there's health checks in Kubernetes, something called readiness probes. So how do you make sure that your pods are actually running and healthy? You create something called a health endpoint with the path and port you want, and you provide some kind of configuration. And Kubernetes will ping these endpoints once in a while, and then if it determines that your pod is not, this is readiness. If your pod is not ready, then it will kill it because it's not healthy anymore. Otherwise, it will just say, okay, this pod is healthy, and it will let it run. Sometimes you want to make sure that so by the way, this is liveness probe. So that's what I described. I don't know why the slides got reversed. It was liveness and then readiness. So, but then in some cases, your pod is healthy, but it's not ready to serve traffic yet. Because, for example, let's say your pod is running, but it needs some state from some database before it can serve traffic. So for that, you can create a readiness probe. Same way as before, like you create a path and a port and some configuration, and Kubernetes will ping that, and then it won't serve traffic until you're ready, basically. And once you say okay, then it will start serving traffic to it. So that's the first one was liveness. This is readiness. The slides are out of order for some reason. There's also a dashboard in Kubernetes by default that shows you your deployment and your pods and your replica sets and everything that you can run. There's daemon sets. So pods can live anywhere, right? They can live on any node. There's no guarantee that a pod will live on a certain node, right? But there are use cases where you want to make sure that a pod lives on every single node in your cluster. So for those use cases, you want to create what's called a daemon set. So you create a daemon set. This way, you are making sure that this pod will live on every single node. And maybe you want to do something special in that pod. You want to do audit logging or some kind of checks on every single node. For those use cases, it's perfect. So that's what you do. Pods live forever. And if they die, replica set will look at it and create a new one. But sometimes you don't want that. Sometimes you want to basically create some pods, do some job, calculate something, and then kill those pods, right? You don't want them to run forever because you don't want to pay for them forever. So for those use cases, there's something called jobs. This way, the pods are created depending on a job, and then run the job, and then once you're done, the pods will go away. Okay? And so this is basically perfect for batch processing kind of situations where you just do some kind of processing, and then once it's done, your cluster goes away. Pods don't have state, usually, except the persistent disk that get attached to it. And also pods can start in any order. So let's say you have pod A and pod B and pod C. There's no guarantee that in what order they start. But sometimes you want to have some kind of state in your pods, and sometimes you want to make sure that pod A starts from before pod B. So for those use cases, there's stateful sets that you can create where you can specify this kind of stuff. And then configuration. We always think about code, but actually configuration is a big part of your application. So in Kubernetes, there's something called config map. You create it in a central place. So these are key value pairs for your application. And when your pod starts, it will get a volume that gets attached to all the configuration. So the pod will have all the configuration. Every pod will get a volume with the configuration, but your configuration lives in a central place in config map. And same thing for secrets. So if you want to have certificates and secrets, stuff like that, you can create in a central place called secret. And then when the pod starts, it will get a volume with the secrets as well. So all this stuff that you need to worry about yourself, Kubernetes provides you the building blocks to do it properly. Yes, that's it. As I mentioned, there's even more stuff. So if you want to learn more, go to kubernetes.io. I'm going to post the slides on my Twitter. So if you want the slides, just follow me on Twitter. And I don't think we have enough time for questions, but I'm going to be outside the room after the talk. So if you have any questions, just find me outside and we can chat about it. So thanks very much for your attention.